Okay, everybody, we are on section 3.5. It's on page 320 if you want to join us there. Before we start on this section, I want to remind you of this. This is the most important thing you learn this chapter, even though you don't believe it yet. It is. If I have y equals a to the x, how do you change that to a logarithm? What's its equivalent form written as a log? Of y equals x. It was the invention of these that allowed us to get at this and figure out what it is by making this change. These are equivalent forms. Okay? So, if I have something like this, let's say it was this. In a general way, without giving me any specifics at all, how would you go about solving that? Graphing is an option. That is not the option today.
You would put it in the other form.
What would you name it? What would you call this form right here? This is exponential form, right? That's exponential form. So this is the form that it's in here. It's called exponential form. I think it's obvious why. This is called logarithmic form. Log R is mic form. I haven't got my eyes. Okay, so to get at this x right here, you would. It doesn't matter what kind of log. Natural log would be best here because the natural log of b is 1. But you could very easily do log base 3 if you want, which would be dumb, but you could, as long as you do the same thing to both sides. So what we say when we have something like this is, when I say, what do you got to do to this? Or what should we do to this? You would say, change it to a log. That's what you would say to me. I need to change that to a log. Right? How do you handle something like this? What do you do?
Change it to a log.
Change it to a log. Good. What about this one? How do you handle one like this? Change it to an exponent. That's exactly what you do. Change it to an exponent. Whatever you've got as an equation, whatever it is, if you can identify what it is, change it to the other. But there are usually some things involved first before you can do that. For example, on this one right here, before you change it to a log, which is what you got to do, change it to a log, you got to get the exponent part alone first so that it looks like this. Then whatever crap is over here, you change that to a log using it. So you would first divide by 3, 7/3. And then you would log 7/3, natural log 7/3 equals x natural log of b. You would log both sides, right? Or if you had if you did it that way, it would be 7/3 equals e to the x. You could also say, I've got one of these, how do I change it into this? Rather than thinking of logging both sides, although that's also an option, you could log both sides. Let me show you both ways. You log both sides, you get the natural log of 7/3. We chose natural log, I hope it's obvious why. Anybody have trouble with that? Because that goes to 1. So x is done. That's what happens if you log both sides. Could you also change this thing to an x or to a logarithm? And if you did, what would it look like?
Natural log.
So it would be log base e, right? Yeah. Of 7/3 equals. Voila! Look, it's the same thing. It should be. It's 2 different ways of solving the same equation. To do this one right here, what would you do? Ultimately, what are you going to do to solve this? Excellent answer. Change it to a log. Now, what do you got to do first? Divide by 4. So to do this one, you would first say 10 by division equals 3 to the 3x. Could you log both sides of this? Which log? Doesn't matter. Doesn't matter. You got 2 keys, pick one. If you were to log both sides of this, if I use natural log, I like natural log better. We never use anything but natural log in calculus, so that's my default. I would say the natural log of 10 divided by 3x, natural log of 3. Did you catch that? And so to solve for x, you can do it in one move. If you understand you got 3 things multiplied here, we need to divide by the 2 that are not x. And so I would divide both sides by 3, natural log 3. That would take care of that and that, leaving me with x. And then I would calculate. Make sure you wrap this in parentheses and make sure that you close this parenthesis and this one both. Yeah, you following? Okay. So this one right here, we would, ultimately, what are we going to do to this to solve it? Change it to an exponent. But what do we got to do first?
Gotta get the next side, like on the side.
We got to get the log by itself. By doing what? Get rid of this. Pardon me? Division. So the first move is to do this. Log base, keeping in mind, in the back of your mind, right here, well, up close where you can grab it, we're going to eventually change it to an exponent, but not till we've isolated the log, which will be 7/3. Then what? How do you change this to an exponent? Now we do have to rely on it. When we had something like this, we could log both sides, and that's what I kind of defaulted to. But now that we've got a log, we've got this situation here, it has to be changed to an exponent. How do you do that? No? Okay, I heard that first. Did you say x equals?
Yeah.
All right, x equals, and grab your calculator. Make sure you put this in parentheses. See how it isolates the thing you couldn't get at? How it isolates it by going to the other form? That's the nature of inverses. Inverses undo things that are in your way. And logs and exponents are inverses. So if you have a log equation, eventually change it to an exponent. If you have an exponent equation, change it to a log by logging both sides. See what's going to happen? That's what the title of this is, says equation solving. Both exponential and logarithmic. This is your best buddy here, except for when you have something like this, it's a little bit easier to just log both sides, but you get the same result. Change it to a log or log both sides, you get the very same thing. Look, we got this here by logging both sides, and we get the same thing here by changing it to a log. Moral of this story is for both of them, get the log or the exponent by itself first. Then change it to the other. Okay, so look at example 1. They've got an equation for us there. What's the ultimate strategy? Change it to a log. Why are you going to change it to a log? Because it is an exponent. 20 times 1/2 to the x over 3 equals 5. 20 times 1/2 to the x over 3 equals 5. Ugly? Not very hard to handle, as long as you understand the path you're going to take. So first thing we got to do, divide by 20. So I get 1/2 raised to the x over 3 equals 1/4 if you reduce it. Do you all agree? Then what? Log it. And logging this side, it brings this guy down here where we can deal with it. I'm going to use natural log again. You use whatever you want. What I just did there is log both sides and applied that exponent property to bring this down. Everybody clear? Okay. So now I've got, if I go to get rid of this next, this is just a number. When I go to get rid of that next, it's going to leave me with x over 3 equals the log of a 4th. And at this point, if you want to write it as a decimal, it's easier to put in your calculator. So you don't have to use parentheses, but whatever. And over the log of 1/2. This is just a number, right? How are you going to find out what x is? Yeah, whatever you get here, multiply by 3. It's a cross multiply kind of thing. Get a number here, and then it will be x over 3 equals a number. Some number. So cross multiply, x will be that number times 3. Not so bad. If you have a strategy where you're headed. If it's an exponent, you will eventually log both sides. If it's a log, you'll eventually change it to an exponent. Once you isolate it. Got to isolate it algebraically. Okay? Do you think you can handle exponential ones? I've got 3 other examples I can do for you if you want to see them. You want to see them? 12, 14, and 16. Let's look at those.
thought you were meaning examples. I was like, good grief.
Oh, yeah, no. Number 12 says 0.98 to the x equals 1.6. 0.98 to the x equals 1.6. What form is this in? What are you gonna do to it? Change it to a log. And are we ready to change it to a log right now, or do we have to do something? We're ready, because the exponent's isolated already. So we're gonna say x, natural log of 0.98 equals the natural log of 1.6, because we're logging both sides. So now it's a simple division. Done. If you use your parentheses right. Don't get to where you're typing so fast you're not watching and closing parentheses where they need closing. That's what a lot of mistakes people make. That
Do
was
you want us to write the answer in like decimal form instead of the?
typically when you're doing logs and exponents, yes, decimal form is great. 4 places, 3 or 4 places is typical, because quite often when we do exponential actual modeling with story problems, the exponent, the thing that's sitting right here, is extremely sensitive to change. You can make a big change in your answer with a very small change in this. So that's the reason why we're really accurate. When we're solving for x and it turns out to be a decimal, we want to have 3 or 4 places. That book of tables I have has them to either 4 or 6 places. So round them long. Put a lot on, okay? All right, so there's that one. That's number 12. Here's another one. 80e to the 0.045x equals 240. 80e to the 0.045x equals 240. This is very, very typical when you're talking about things that are either growing or decaying naturally, because that e is in there. And you always get a beginning amount and a rate at which it's decaying, or this one's decaying. I think it's decaying. And maybe it's growing. Maybe it's growing because that's positive. And then equals some value after this much time. This is really typical. This is where you really got to be good at using your skills. And it's not very hard. We've seen it. First thing we got to do is, we got to divide by 80 before we do any. And by the way, what are we going to change it to? A log. Good. Okay. So it's going to be e to the 0.045x equals 3. Now, natural log, even though I've chosen it to do every other problem, it's a really good choice here, because when I do this, 0.045x natural log of e, that goes to 1. I don't have to worry about it. And over here is the natural log of 3 because I'm logging both sides. So x is going to be the natural log of 3 just over 0.045, not the log of it, because the log part went to 1. Let me break that out. Round it. It was an exponent. It was a piece of an exponent of 3. You round it to 4 places typically. Everybody okay there? Do I need to do 16? 16's got another little quirk to it. I'll show you 16 also. 16 says 7 minus 3e to the negative x is 2. 7 minus 3 e to the negative x equals 2. What are we going to change this to? Change it to a logarithm, but not yet. What do we got to do?
Subtract 7 first.
We got to divide by 3 next, good, or negative 3. Then, natural log of, which would give me negative x on this side, equals the natural log of 5/3. Do you agree? Right? Because I've already eliminated the log e. Everybody good? Okay. So x then is just going to be the negative natural log of 5/3. And then you write that out. Not so bad, right? Wait till you see what's coming next.
Oh my goodness.
It's going to be fun. And it's not going to be changing logs to exponents, not yet.
So
We're still dealing with the exponents. What?
when you're plugging like the log in the calculator, can you literally just do like negative log?
Yeah.
Will that work?
Mhm.
You have to put it
Yep. Yep. I'm going to be staying on this board for the sake of recording this, folks. So if you want any notes on anything and you see me start to erase, stop and get your phone out. Otherwise, it's all going to disappear. This next one, I got to suspect that I'll have to take a picture of it because it's complex. Okay? It's got a lot of math in it. You're aware of and can deal with all the math in it, but it may not occur to you if you did it cold how to handle it. So I'm going to show you, and you will have 1 or 2 on your exercises to do, and you will definitely have one in your next test. So you want to pay attention to this really carefully. And if you get lost, or your mind wanders, or you just, ask me, stop me, we'll go back. You have to get a handle on this. This thing that we're going to do has to do with an interesting notion in trigonometry called hyperbolic sines, cosines, and tangents. Go on. Yeah, you should. It's awful. But when you're actually taught that in trig or in calculus, these hyperbolic things, what the equation is that we're going to be dealing with, maybe you'll be able to remember from the back of your mind, oh yeah, I remember how to deal with that. Or, oh yeah, I've seen that before. At least. Here's what it is. This has to do with a very specific branch of, it's not even a branch, it's more like a twig of mathematics, having to do with hyperbolic trig functions. They don't mention that to you here. Or maybe they do and I haven't read it. Yeah, right there, yeah. See right there to the left of example 2. Let's read this for just a minute. Just so you get a feel, hopefully it'll stick in your memory a little bit. To the left of example 2, right there underneath that purple word says a cinch. You see it? It says you may recognize the left-hand side of the equation in example 2. So you're looking at example 2 and going, ew, that's gross. You may recognize the left-hand side of the equation in example 2 as the hyperbolic sine function. You may not recognize it. I'm telling you, that's what it is. Hyperbolic sine. That was introduced in exercise 59 of section 3.2. Did we do 3.2? I probably skipped it. This function is often used in calculus. We write SINH, meaning hyperbolic sine. Again, it's the reversal of the adjective in the noun. Hyperbolic sine of x equals e to the x minus e to the negative x over 2. And that symbol, SINH, is pronounced sinh. And cosine, hyperbolic cosine, which is COSH, is pronounced cosh. And it's really weird because hyperbolic tangent is pronounced tang. Really weird. They put an H on the end of tangent. You got TANH, and somehow or another that people call tang. Okay. All right, so what we're going to do is we're going to take this expression for a hyperbolic sine, which is this. Oh, no, it's okay. No, continue working, you dumb thing. Hey. Okay. Yep, we're going to be able to see this. Okay, so this is the hyperbolic sine part. You don't have to remember that it's called the hyperbolic sine for the test. You just have to be able to work with this strange fraction. Okay, so our objective is to, because of that equal sign right there, our objective in this thing is to solve for x. And it's quite a leap from what we've just been doing to do it here. So please pay attention. Either take some notes, or when you're done, make sure you take a picture, because you're going to want to refer back to details when you have to do it yourself. First thing I would do is the easiest thing of all, which is to cross multiply. Is that okay? So the first move is to write e to the x minus e to the negative x equals 10. If you can get this far on your test, you will get no points at all. Just so you know. That's the easiest thing in the world. I know. Okay. Now, this is kind of a problem because people don't like dealing with negative exponents. It's really bad when it's a negative variable exponent. So we're going to deal with that right now, based on what you know. This one's okay for the moment. This one should be written 1 over e to the x to at least make it positive and see what we got. So this move from here to here is just to make exponents in their individual terms positive by putting them where they're not. You with me? Then we see, okay, well, we got rid of that problem, but we bought a new problem. Now we got fractions. Multiply through.
Okay.
Multiply through by the common denominator. That's how we're going to eliminate the fractions. We're going to multiply through by e to the x, because that's the only denominator, so it is surely the common one. Everybody clear? When we distribute that e to the x through to every term, we get this. We get e to the 2x. Now you think about that before you say, now what? Minus 1 equals 10 e to the x. Because when you multiply two things with the same base, you add the exponents, and x plus x is 2x. What? And then e to the x times 1 over e to the x is 1. That's why we did it, right? They canceled. And then e to the x times 10, that can't be handled in any way, so it's just 10 e to the x. You okay? Everybody? Okay, so now I'm gonna pull a little sneaky here, and you're gonna go, just listen, just wait a minute. You may not yet, but I recognize this as being quadratic-ish. Can you see that it's kind of quadratic-ish? It's got three terms. A term here, a single term here, and a constant here. You see it's kind of quadratic-y? So I'm going to put it in standard form as a quadratic. It would be e to the 2x minus 10 e to the x minus 1 and set it equal to 0, because that's what we do with quadratics. So if you recognize it's quadratic, put it in standard form, set it equal to 0. That's the next move. Y'all clear? Now's where it's going to get kind of...
Oh, do we have a quadratic formula then?
Yes, because it will not factor.
Oh dear.
It will not factor.
Yeah.
Oh, it's not too
Wait,
bad.
could you play?
I'm gonna rewrite it one more way. I'm gonna rewrite it slightly differently one more time to clearly show you what we're looking for here. This is actually e to the x squared, isn't it? Isn't that another way to write that?
Yeah.
Minus 10 e to the x minus 1 equals 0. So while this is not truly quadratic, it is quadratic-ish. What is the quadratic variable in this equation? It is e to the x. It's the thing that's squared here, that's single here, that doesn't show up here. E to the x is your quadratic variable. Now, can you identify a, b, and c so that we can use the quadratic formula? What's a? 1. The quadratic variable is e to the x. What's its coefficient? 1. What is b? And c? All right, then you need to clearly be able to identify that. First of all, you got to know what the quadratic variable is. You know how when we do quadratics before, and they're true quadratics, we write down x equals, and then we start doing negative b plus or minus blah, 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 blah. Well, guess what we're going to write here? E to the x equals 10 plus or minus the square root of 100 minus 4 times. Remember, this is where the a comes in. It's important. AC is going to be negative 1 over twice a is 2. We clear? Now we clean it up. And we have 100 plus 4. Okay on that?
Yeah.
Does 104 have any pairs in it? Yes, it does.
Yeah.
Pairs, I was meaning
52 and 2.
Yeah, 26 and 4.
There you go. That was better. Yeah.
So this one would be 10 plus or minus 2 root 26 over 2. Do you agree with that? Because 104 is 4 times 26. You would find that if you prime factored. Okay? Take a 2 out of everything, and I now have that e to the x, not x. You're not done here. E to the x is equal to 10 plus, no, not 10, 5. Sorry. 5 plus or minus the square root of 26. Okay?
Then we have to plug it back into the original.
Now we have to change this exponential equation to a log. Use natural log on both sides. It's going to be x, natural log of e. Can I just do that? Everybody okay with what I'm doing? Equals the natural log of, because we're logging both sides, 5 plus or minus the square root of 26. Now, how big is the square root of 26 about? I mean, just give me an idea.
About 5.
A little more than 5. Right? If you have 5 plus a little more than 5, you get a little more than 10, right? But if you have 5 minus a little more than 5, you'll get a negative. Small, yes, but negative. And you can't log a negative. So we will eliminate that as a possibility. And so the final answer is whatever the log of that nasty little beast is. Round it to 4 places.
2.3124.
2?
Yeah.
2.3124.
2.24.
Put a dot over things that are approximate to give your reader an indication that you know it's an approximation.
A dot over the equal sign?
What's that?
A dot over the equal sign? Is that what you did?
Yes, over the equal sign. This is the way they print approximately in the book. But the reason I don't like that, and this is also acceptable, it's well known, is because I'm busy solving, and say equals. And I get to the end and say, oh, that was an approximation. I do not want to take the time to erase that and write that. I just slam a dot on it and I'm done. That indicates to the reader very, very quickly that I know that this is an approximation as the doer of the problem. Yes, you can take a picture in just a moment. I'm going to make a comment right here. I'll do it in the color so that it doesn't look like it's part of the problem. And I'm going to say eliminate. Now you don't do it every time. You got to look at both of them, see if they're both positive. If 5 plus this is positive and 5 minus this is positive, you got to get 2 answers. But we rejected the negative. I'm going to say reject. Reject numbers that make you log negative. So maybe you'll remember if you put that in your picture, maybe you'll remember why we're only considering that one. You have to consider them both. Quite often we throw the negative out, but not every time.
Who's going to be the one to send it to Lynn?
So the E is like about 2 points.
I didn't understand it.
Was it here like equals? Okay, so.
Just don't worry about it.
From the arrow part on the first?
Yeah, from here to here.
Yeah.
Okay.
That's right.
I took e to the x times e to the x. When they have the same base, you add the exponents, and x plus x is 2x. So I took this times this, and I got e to the 2x.
Oh, okay.
Then I took this times this, and this was in the top, and this was in the bottom, so it was 1. That's why we're doing. That's why we're multiplying by this, is to eliminate this. Yeah, you sure you got that?
Yeah, it was just the first, the 8 of the 2.
If you take the time to write this quadratic thingy like this, then whatever is squared here and whatever is single powered here, which is this, that's your quadratic variable. Normally this would be x squared minus 10x minus 1, but it's not. It's e to the x squared minus 10 e to the x minus 1. So the thing that's squared here and single here, that's the quadratic variable, we call it. It's not x, it's e to the x.
Actually,
It's being squared.
That's our whole variable. Okay.
That's the variable that
instead of
we
x,
use the
it's
quadratic.
e to the
Yeah, and the way we decide A, B, and C is, once you recognize this whole chunk here is the variable, what's its coefficient? 1. Negative 10. Negative 1. That's A, B, and C to use in here. But what you're solving for with the quadratic here is e to the x, not x. Right, so when you get to here and you know what that is, you simplify it as much as possible, you still got to solve this exponential by logging.
That makes a lot more sense.
All right,
will
but
you write a 1 in red right there so I make sure? Because I think I'll forget that.
1, and if you want, I'll say this is A,
Yeah.
B,
Well, we did.
D,
Wait, that's just that.
C.
Not so.
Yeah, perfect.
Okay, all right. Okay, that's a tough one, but it's one you're gonna have to know how to do, so make sure you practice it. There's 2 or 3 on the exercises, and if you need more practice before test time, I can come up with it. They're pretty easy. All you gotta do is say, that thingy equals 8. That thingy equals, don't make it equal a negative.
Wait, will it always be that thingy on the one side?
No,
No?
it may be, instead of E, it may be 15 to the x minus 15 to the e to the negative x over 2. It may not be E for your constant, it might be another number. But it will be some number to the x minus that same number to the negative x over 2.
So then the 1 wouldn't apply then, it would just be 15, right?
No,
What?
would still be 15 to the x here, and that's your quadratic variable. So that by the time you get here, it'll be 15 to the x, and then you would have to log both sides and divide by the log of 15 before
So
you.
your A would still be 1?
You can't get
And the
rid of
quadratic variable would be 15 to the x. Instead of writing e to the x equals this junk over here, you would write 15 to the x. Whatever this is here, that's what's going to be equal at this point. Yeah.
Okay.
It's not crap. I mean, it's not that hard. I understand why you're saying crap.
Complex, not difficult.
Complex.
Well,
Involved. It's very involved. But all the skills, you have all the skills already. You just recognize where they are, okay? That takes a little practice. Okay, ready to go on? Okay, we've practiced now. This is the toughest type of exponential question or equation that you'll solve. But it is an exponential equation. Can you see from the outset this is exponential? And can you see at the very end we had to log it to get it solved?
Yep.
Okay, so we've solved exponentials quite a bit so far today. Now we're going to solve log equations. And I've already talked to you about how. We're just going to practice it in several different situations so that you can handle them all. All righty, here we go. So we are at the red words on page 321 near the bottom of the page says solving logarithmic equations. Okay, so the very first one we've got there is log x squared equals 2. This is already going to throw a little quirk in things. It's not nearly as bad as what we just did. Oops, can't spell logs. Log x squared, did I say equals 10? Was it equal? 2. 2? Oh, equals 2, okay. So we've got, as the presentation of the problem is a log, what do we got to do? Change it to an exponent. Have we got, are we ready to do that right now? Yeah, because the log stands alone, right? Okay, so how are we going to change it to an exponent?
X squared.
So, okay, I'll do that. I can do that.
Oh, equals 2. No.
I heard it.
10 squared.
10 to the 2.
As the basis.
See that 10 right there? Can't you see that 10?
I saw it. Why do I
Oh,
see
silly goose, it's a log base get.
If there's no base, it's base 10. And you've got to default to that with your own head. You see, so everybody sees that 10 right there. Do you see it?
Yes.
So it's 10 to the 2 equals what we're logging. That's what we got here. Okay, what is 10 to the 2? So what is x? Plus or minus 10. Do both plus and minus 10 work if we plug it back in? Because we can't log a negative. But do they both work or not? Yes, they do. Because you're going to square whatever the number is before you log it. Both of these are solutions because 10 squared is 100, but so is negative 10 squared. So you're logging a positive in either direction, so you have to be really careful there. Now, there's a funny little quirky thing that goes on with this kind of a question. What if, let's see if we've got it on the other side. If you attack this, or if you tackle this problem, I'm going to write it down again. There's going to be a problem here that you need to be aware of. It's extremely subtle. You know what subtle means, right? Hardly noticeable, except for it's really important. Okay? If instead of what we did there, which is to change the log to an exponent, if instead you decided to apply the property that says that I can take this exponent on what I'm logging and put it down front here, then what you would have is this, 2 log x. Is this a legal thing to do? It is. It's a legal thing to do. Divide both sides by 2, and then you've got, if you change it to an exponent at that point, you've got 10 to the 1 equals x. So 10 is equal to x. And you're missing half of the solutions. So which one is correct? This one. Moral of this story, resist the urge to use that property when you're solving a log equation. Get the log isolated and immediately change it to an exponent, and then you won't miss any solutions. But this one leaves one out. So don't apply that little rule. As soon as you got the log isolated, take this base to this power equals this stuff. Then you're still solving for something squared. And you do have to remember this, but you've been this for a long time. The process of solving, you need a plus minus sign. If you forget that, you're going to be missing half the solutions too. But this is up to you to remember. This doesn't ever call for it.
So if it was like an actual log,
What?
would it be different?
Nope. Nope.
It would still just be x squared equals what then? Equals
X
10?
squared equals e squared. Whatever e squared is, then you would square it. That would be plus or minus both of them.
Okay.
And it would be an ugly decimal because e is irrational. But still, handle it the same way. They gave you nice numbers so that we could focus on the process again. But it would work just as well as law, natural law. Okay, here comes the next one. It is natural logs. Remember that's what's natural logs based? Remember you can see that E, really? You can? Okay, here we go. Natural log 3x minus 2 plus the natural log of x minus 1 equals twice the natural log of x. Something weird's going to happen here. Stay with me. It seems like every problem's got a little strange little problem in it. So stay with me on this. This is a logarithmic equation because it's got logs in it, not exponents. There's not a single exponent in there except for logs or exponents, but it's written logarithmically. This is where the skills you learned yesterday come in really handy. We need to condense that left side into a single logarithm. You're going to be using that skill. Condensing a lot more than expanding, but condensing, you're going to be using that a lot. So this over here is the same as what?
Log and multiply those two?
Yep.
So
You don't have to do it in your head. Just tell me what you want to multiply and we'll do it later.
X minus 2.
Okay. You understand that condensing? And I'm also going to apply another property here, and I'm going to say that's the log of x squared. Okay? Now, without looking at this, because this is really complex, just think about this with me, this idea for just a minute. Just think about this idea. If you've got the log of something, say, the log of the log of red, and it equals the log of blue, then what do you know about red and blue? They got to be the same. Because if you log two things and the results of logging them are equal, then the things you logged have to be equal, or that can't happen. So the next step I'm going to do is nothing mathematical. It isn't math. It's not canceling. It's not dividing out. It's not any of those things. It is reasoning. That's what I just tried to talk you into, is to reason this through. If the log of this mess is equal to the log of this little mess, then the messes are equal. And the next step is going to leave the logs off entirely. They did not divide out. They did not cancel. They didn't anything. It's just saying, if the log of this crap is equal to the log of this crap, then the craps are equal. And that's what we write next.
You just take one log off. Just gone.
Yes, but it's not a math move. It's a reasoning move. It's a logic move. If the log of something equals the log of something else, the somethings are equal. They have to be, if the logs of them are equal.
Sure.
That's what we're saying. That's reasoning.
Yes.
Okay. Just get it out of your head. Those logs did not divide out. They're not factors. There's not the log times any of these things. It's the log of them. These did not divide out. They were left out because the things they were logging have to be equal. All right, so let's multiply this through. It's going to be 3x squared. This is going to be minus 3 minus 2, which is minus 5x, plus 3 equals x squared. Got a quadratic, bring it over. 2x squared minus 5x plus 3 equals 0. And we got 4 choices.
Plus 2 plus 3.
What?
3x squared minus 5x plus 2.
Yes, thank you. I'm always thinking ahead and always missing what I'm on. I got to knock it off. Thank you. Thanks, good catch. Excellent. Oh, got to change this too.
Yeah, I was like, wait a minute, hold on.
Well, no, don't change it, thanks. Okay,
I was like,
sorry.
how did that?
Sorry. Now we're all convinced things are good. Well, are we safe? Are we good here? Good. Now, do you think that'll factor?
Probably.
Well, what I'm saying is you got four choices now. That it's quadratic, you got 4 choices. You can name them. Name them for me.
Polyroot.
We could graph it. Polyroot. Factor it. Quadratic formula. 2 are algebraic, 2 are calculator. Because I don't have my calculator handy and I happen to know this will factor, I'm going to. Because I can see this 2 and this 2 is going to give me the 4 I need, plus the one that's right there is going to give me 5.
Oh. Yes. Wow.
See?
What's it like to be like that?
I don't know because I don't know any other way.
Oh, wow.
So, x is either what? X is either 1/2 or 2. And your polyroot finder would have told you that. Okay. All right. Now the question is, do they both work? How do you find out? You go clear back to the original, way back to the original. There are 3 logs in the original. If either of these make any of those logs log a negative, we throw it out. 3 times a half is 3 halves. That's 1.5 minus 2.
That makes it
Negative.
Negative. Reject.
Gone.
Plug the 2 in. 6 minus 2 is okay. 2 minus 1 is okay. 2 is okay. We'll keep that. When you do this on your final, folks, if this happens, and it will, if you decide to reject one or both, I want to see the solutions and see the ones that you rejected by crossing it out. Don't just give me the nice, clean answer, because I don't know from that answer whether you ever considered the other one or not. And I need to know that you considered it and rejected it, if it's going to be rejected. You may end up keeping them both, but I need evidence that you checked them.
So if both are rejected, just say no solution.
If both are rejected, yep, right. No solution out there. But if one's rejected and one is kept, I suggest you circle the one you like and throw out, so that I can see through it. Throw out the one you don't want, yeah.
How did we know to reject the 1/2?
Because we go plug it into the absolute beginning equation. And if it causes, in these 3 places, if it causes us to log a negative in any of these 3 places, we throw it out. 3 times that half is 3 halves. That's 1.5, and 1.5 minus 2 is negative. Gone. If it had passed this test, we check it here. If it passes this test, we check it here. If it fails in any one of these 3 places, we throw it out. It failed first right there. We had to check this one here, here, and here, and we were logging a positive in all cases, so we'll keep it. You understand?
Yep.
Okay. So this 1/2 is a solution, but it's extraneous. So to get from here, folks, from here to here, that's a reasoning move. If you got logs on both sides, you may drop them, but it's nothing mathematical. Okay, let's try one that doesn't have logs on both sides. Okay, listen up. Shh. Have you ever heard of anybody talk to you about orders of magnitude? For example, $100 is on the order of magnitude 3 greater than a dime. How many dimes does it take to make $100? 1,000, right? Isn't 1,000 10 to the third? It's the 3 I'm talking about. $100 is an order of magnitude 3 greater than a dime in value. Because it's 10 to the third dimes that makes $100. You follow that? Trying to think of something else. Quite often they will talk about orders of magnitude when they're talking about distance between planets, or especially distance between stars. Orders of magnitude. Like, for example, the speed of light is what, 186,000 miles per second?
Sounds about right. Yeah.
What? 186,000 miles per second? Meters per second, 186. That's on that's the order of magnitude 6. No, 5. Because 100,000, we're talking about 168,000. But the size of the number is a 10 to the 5th number. It's 100,000. 10 to the 6th would be a million, right? Order of magnitude 6 numbers are in the millions. Orders of magnitude 10 are in the tens of billions. Order of magnitude -4 is 4 10,000ths. Very tiny. I mean, 1 10,000th, really tiny. So when your order of magnitude is negative, you're talking about teensy things. Order of magnitude positive, you're talking about gigantic things. And it's powers on 10 that are orders of magnitude. That's all I'm going to tell you about that. The Richter scale, as I told you yesterday, although we didn't talk this language, the other day when I was telling you about the Richter scale for earthquakes, an order of magnitude, a 7 is much more destroying, has much more destroying power than a 4. Do you remember me talking to you about that? Yeah. A 4 can barely be felt, and not by everyone. A 7 will break up roads and kill people. Knock buildings over, and pull up highways, and knock over overpasses. And yet the difference between 4 and 7 is hardly anything, unless you understand we're talking orders of magnitude. A 7 earthquake has, compared to a 4, is a difference of magnitude of 3. That means it's 1,000 times more intense because 10 to the third is 1,000. Richter readings are orders of magnitude on 10. So, you kind of follow that, see if this doesn't follow through. Example 5 says, how many times more severe? That means intensity, it means energy, means shaking power, means destructive power. How many more times more severe was the 2001 earthquake in, and I looked this up and had the computer pronounce it for me, Gujarati. No, Gujarati. Gujarati. The earthquake in Gujarati, India, which had a Richter reading of 7.9. How much more times more intense was that than the 1999 earthquake in Athens, Greece, which was a 5.9? Order of magnitude 2. You see the difference? The order of magnitude difference is 2. So how much more shaking power did it have? 100. And look at that right there. Now, that was easy because they were both 7.9. One was 7.9, the other was 5.9. What happens if they have different decimals? Like, what if one earthquake was 9.3 Richter reading, and that's intense. That's killer there. And the other one was, let's say, 4.7. How do you find out how much more intense? And then take 10 to that, yeah. Here's another thought. If you can understand what I'm saying, then yeah, you take 9.3 minus 4.7. What is that? You do not say that it was 4.6 times more intense. It was 10 to the 4.6 times more intense. Because that's the order of magnitude difference, and it's 10 raised to the order of magnitude that tells you how much more intense. So you'd actually have to calculate this, 10 raised to the 4.6 in your calculator, and give you a number. It's big. What is it? Read it. One digit at a time.
39,810.717.
There's a 3 in front of the 9.
Okay, so you would say it's 39,800 times more intense, about. More energy, that much more energy. Here's another way to think about it if you want. This is, I'm not going to tell you what my actual age is, but if you wanted to know how many times older I am than you, what would you do? You would subtract? I wouldn't. If I want to know how many times more old I am than you. Divide what? Yeah, my age by your age. I'm not going to tell you what that is. If you want to know how many times more intense an earthquake is, then what you're really doing here, yes, this is a way to do it. If you understand this, do it. Great. But don't answer 4.6. That won't do it. If you want to know how much more intense this earthquake is, which is really what the level of energy that's associated with it, is compared to this, you would take the bigger one divided by the smaller one. But you got to understand, these are orders of magnitude, and they belong as powers on 10. So you could take 10 to the 9.3 divided by 10 to the 4.7. For the same reason, you would take my age divided by your age. If you want to know how many times more intense this is than this is what the division is. But it requires you to subtract these. I mean, if you got things with the same base you're dividing, you subtract the exponents, right? You just need to understand that that is 10 to the 4.6. And you can either do that by subtracting these, but make sure you take 10 raised to it to answer the question. Because the answer is not 4.6. It's 10 to the 4.6. So either way you think of it, that's what you have to calculate, and this is the answer you will get either way. So keep that in mind. The author goes to way, way more detail than is necessary. So don't look at that, look at my example.
So that you tell me this. It's like a
I'm going to come back tomorrow and talk to you about pH and the base 10 scale it is. pH tomorrow. We're not done. Don't settle in. I got to show you two more things. Hold on. I'm also going to talk to you about Newton's law of cooling, which is also an exponential function. That's exponential, and pH is a logarithmic one. But I don't think you've had enough experience solving log equations yet to be able to handle that on your exercises. So I'm going to show you a couple of those, and then I'll quit. We'll come back and finish it tomorrow, so you won't have anything new, but we'll finish up this exercise here. You can get started on the review anytime you decide. You find some log equations we've got to solve there. I think I assigned them. I'm going to make up some log equations up here. Do not expect them to come out pretty, because they're being made up. Okay? So let's say we had the log base 3 of x minus 2 plus the log base 3 of x plus 4 equals 12. I have no idea how this is going to work out, but it's the process that's important because they made them work out a little nicer than mine did. We got a problem here because remember the one that I erased right there that had logs on both sides, so once we condensed them, we dropped them? That's not the case here. We've only got logs on one side. Still needs condensing. How do you condense those two together?
Log base 3 times x minus 2.
All we did there is condense the left side. Why do we do that? So that there's only a single log on one side or the other. Got to get single logs before you can drop things, and can't drop it here because I got a log on the right side. Now what? From the beginning of the lesson, now what? Change it to an exponent. Those are the words. Change it to an exponent. Change it to an exponent. If it's a log, change it to an exponent. What are you going to do if it's a log?
Change it to an exponent.
All right. How do we do that?
X minus 2 times x plus 4 equals. Is it 12 to the 3 or 3 to the 12?
Which one?
3 to the 12.
3 to the 12. Okay, I want to change my mind since I made this up. I do not want to deal with 3 to the 12. We'll change this to 4. Okay? I don't want to do 3 to the 12. That's what you know. Okay, so now what I have is, I got to FOIL this out. It'd be x squared plus 2x. Check me on this. It's minus 8, right?
Yes.
Yes.
Okay. Minus 81. Because that's what 3 to the 4th is. And it's quadratic, so I'm bringing it all over.
I was confused. I was like, I don't think 4.
X squared plus 2x minus 89. Think that'll factor?
No.
If you do, think again. That 89 is way too big. So what are you going to jump to?
Polyroot.
Do it quickly. It's because I made this up that it's so gross. But go to polyroot as quick as you can and find me 2 solutions. I think there will be 2 because that's negative and it's quite a ways down. So it's a parabola. It's going to open up way out here and grab everything. Grab a couple of them.
Negative 10.4868 and 8.4868.
Okay. Can you see that negative 10 minus 2 is going to fail right there? Reject that. 8 something minus 2 will be all right. 8 something plus 4 will be all right. We'll keep this one. Now, people, this is important. Because it rarely shows up, but when it does, you'll miss it. People like test questions like that. Myself, and I ask you included. So listen. Listen very carefully. On the next test, you're going to have to explain this. If your explanation is crappy, you don't get full credit. Why did we reject this?
Because that makes you log a negative.
Because it caused us to log a negative. Many people will say we rejected it because it was negative. That is not why. Sometimes negatives satisfy the conditions up here, and we keep them. Rarely, but sometimes they do. Sometimes positives fail the test, and we throw them out. We did not throw this out because it's negative. We did not keep this because it's positive. You'll have to explain this on the next test. We threw this out because it caused us to log a negative in the original equation. We kept this because it did not cause us to log a negative in the original equation.
That's all you're right. Would you have to say like both of them why you kept them and why you?
Yes, one of the questions on the test says, solve this equation and explain,
Why you kept one and why you got rid of one?
well, why you keep what you keep and why you reject what you reject. And it has to do with making us log negatives or not log negatives. Has nothing to do, really, with whether this was negative and this was positive. It's the taking it back to check it that causes you to reject it or not. And quite often, we reject negatives and keep positives, but that's not why we kept them. That's just what happened when we checked it. Do you need to see another one? You think you can handle log equations? You've got to create a single log on one side if it's not already created. If it's already a single log on one side, then you change it to an exponent and continue. If it's not, you condense them and then change it to an exponent. You can do almost all of the exercises. I'm going to come back and demonstrate some science applications tomorrow. Okay? Goodbye. Have a great day.